All right, let's jump right in, shall we? Today we're diving deep into the world of deep learning security with this paper called Towards Security Threats of Deep Learning Systems. A survey.
Yeah, it's a pretty extensive survey.
Yeah. I mean, it covers like a huge amount of
It's
ground.
245 publications.
245
Yeah,
publications.
it's a lot.
Spanning all sorts of different applications, from image classification to speech recognition to natural language processing to malware detection.
Right. And it's not just that. It's the way they kind of put it all together. It's like a framework for understanding the threats and how they evolve.
Totally. And it's clear from just looking at the sheer volume of research in
Yeah.
recent years that this is like a rapidly growing area of concern.
Oh, absolutely. And it's not just theoretical anymore. It's becoming more and more practical, more and more real.
Yeah, for sure. So the paper doesn't waste any time. It gets right to the point,
Yeah.
like laying out the inherent risks associated with deep learning systems, starting with the typical deep learning process itself, right? The training, the prediction. It's vulnerable at multiple points. The data, the model, the inputs, the outputs, everything's a potential target.
Yeah, and they give some real-world examples, too. Like they talk about these commercial machine learning as a service or MLA systems.
Oh, yeah.
Familiar names, right? Alibaba, Amazon, Google, even the big players are grappling with these security issues.
Exactly. It's a real problem.
Yeah.
So let's break down the different types of attacks. The paper lays out four main categories, right? First one up, model extraction.
Yeah, basically stealing a model. Like, imagine trying to replicate a chef's secret recipe just by tasting their dish. That's kind of what it's like.
You're trying to figure out how it works without actually seeing the code.
Right. And the paper digs into three main approaches: equation solving, pathfinding, and model decision boundary attacks.
Those are pretty creative, actually.
Yeah. One example they give that's particularly interesting is Jacobian-based dataset augmentation, or JBDA.
Ooh, yeah.
It shows how attackers can exploit the sensitivity of a model to, like, small changes in the input to kind of reverse engineer the training data. And then they can even craft those adversarial examples.
It's scary how effective it can be. All right, so moving on to the next category,
Yeah.
model inversion attacks. Now, these are a bit more insidious, wouldn't you say?
Definitely. They're about extracting sensitive information from the training data itself. So think about things like, being able to figure out someone's medical history or financial details just by interacting with a model that was trained on that data.
Creepy stuff.
Yeah. And they talk about two main types: membership inference attacks, or MIA, and property inference attacks, or PIA.
Okay, so MIA is like trying to determine if a specific piece of data was used to train the model, right?
Exactly. And then PIA is more about inferring general properties of the training data set, like the overall demographics or something.
Okay, I get it. So it's like a puzzle, right? You're trying to piece together information about the training data just by observing the model's behavior.
Right. And the paper, they lay out this cool 4-step workflow for carrying out these attacks: data synthesis, shadow model training, attack model training, and finally, either membership or property determination.
Yeah, I thought that shadow model thing was pretty fascinating.
Yeah, it's basically a copycat model that the attacker creates to mimic the behavior of the target model without actually having access to its internals.
Right. So they're working in a black box setting. They don't know exactly how the model works, but they can still extract valuable information.
Exactly. It's a real challenge from a security standpoint. You have to think about defenses that can hold up even against these indirect attacks.
For sure. All right, so moving on to poisoning attacks. Now, these are different, right? They're not about exploiting the model after it's already trained.
Right. Poisoning attacks, they're all about corrupting the training data itself. It's like, if you think about a recipe, it's like putting a bad ingredient in the mix so the whole dish is ruined.
You're sabotaging it from the start.
Exactly. And the paper goes into all sorts of different ways attackers can do this. They can manipulate mislabeled data, inject malicious data, even mess with the logic of the training algorithm itself.
And they give examples for different types of machine learning algorithms too.
Yeah.
Right? Like support vector machines, clustering algorithms, even linear regression. So no algorithm is safe.
Right. And what's even more concerning is that they also talk about poisoning attacks in the context of transfer learning and federated learning, where you're using pre-trained models or collaborating with multiple parties to train a model.
Yeah, and that's particularly relevant, I think, for our listeners, many of who are working with these cutting-edge technologies.
Absolutely. And one of the big takeaways from this section is, like, the importance of knowing where your data and your models are coming from. Even if you're training on what you think is high-quality data, you can still inherit vulnerabilities if the pre-trained components were compromised.
So data provenance and model verification, super important.
Couldn't agree more.
Okay. Last but not least, let's talk about adversarial attacks. These are, I think, the most subtle and maybe the most deceptive. They're exploiting the inherent limitations of deep learning models.
Yeah, it's like tricking the model into making mistakes.
Right, and they do it by adding these tiny little perturbations to normal inputs, so small that we humans wouldn't even notice the difference, but the model gets completely thrown off.
And the paper makes the distinction between targeted and untargeted attacks. So in a targeted attack, the adversary is trying to force the model to misclassify a specific input as something else, like, misclassifying a stop sign as a speed limit sign.
Oh, wow.
Yeah. And in an untargeted attack, they just want to cause any kind of misclassification.
Right.
Just make the model mess up.
So it's like an optical illusion, but for AI?
Exactly. And they talk about this concept of LP distance, which is a way to measure the size of these perturbations.
Yeah, the smaller the distance, the more subtle the change.
Right. And then they go into the whole white box versus black box thing.
Oh, yeah. So white box is where the attacker knows everything about the model, right?
Right. The architecture, the parameters, the training data, everything. So they can really fine-tune their attacks. And they talk about all these different methods like fast gradient sign method, FGSM, basic iterative method, BIM, Carlini-Wagner, CNW, elastic net attacks to deep neural networks, EAD.
There's like a whole toolbox of attack strategies.
Oh, yeah.
But what's scary is that they can also launch effective attacks even in black box settings, where they don't have all that information.
Right. So in those cases, they might use things like substitute model training, where they create their own model to try and mimic the behavior of the target model.
And then they can use that to figure out how to attack the real one.
Exactly. And they also talk about this concept of transferability, which is the idea that an adversarial example crafted for one model might also be effective against other similar models.
So it's not just about protecting individual models. It's about understanding how these vulnerabilities can spread.
Right. And what's really interesting is they don't just focus on image classification. They talk about adversarial attacks in all sorts of domains. Text processing, malware detection, speech recognition, object detection, even physical systems.
It's everywhere. So clearly, we've got model extraction, we've got model inversion, poisoning attacks, adversarial attacks. Deep learning systems are vulnerable at so many points. But before we all get too doom and gloom, it's important to remember that this paper isn't just about the threats.
Right.
It's also about the defenses.
Exactly. Yeah. So in the next part, we really dig into all the different ways that researchers are trying to fight back against these attacks.
Okay, yeah, let's get into that.
So the paper makes it clear, there isn't one magic solution.
No, silver bullet.
Right, exactly. It's more about a multi-layered defense, combining different techniques to make your system more resilient.
Okay, so it's like building a fortress. You need multiple layers of defense to protect against all the different types of threats.
Exactly, yeah. So for model extraction attacks, they suggest things like blurring the predictions so it's harder for attackers to, perfectly reconstruct the model.
Makes sense.
Limiting how many queries an attacker can make to prevent brute force attacks.
Okay.
And implementing anomaly detection to try and catch any suspicious activity.
So basically just making it harder for someone to steal your model.
Yeah, basically.
Yeah, what about model inversion attacks? How do we protect that sensitive training data?
Well, the paper talks a lot about data privacy techniques like differential privacy and homomorphic encryption.
Oh, yeah, I've heard of those.
So differential privacy basically adds noise to the training data in a way that still preserves the overall statistics but makes it harder to identify individual data points.
Okay.
And then homomorphic encryption lets you perform computations on the encrypted data without actually decrypting it.
So you can train and make predictions without ever exposing the raw data.
Exactly. It's like working with a shadow of the data instead of the real thing.
Very cool. And much safer.
Right. So it's all about making it much harder for attackers to extract that sensitive information.
Okay, that makes sense. Now, what about poisoning attacks? Those seem particularly tricky because they're going after the training data directly.
Yeah, they are tricky. And the paper talks about three main approaches to defense: data sanitization, algorithm protection, and robust aggregation.
Let's break those down.
Sure. So data sanitization is basically about cleaning up your training data. getting rid of any poison examples before they can do any damage.
So it's like weeding out the bad apples.
Exactly. And there are all sorts of techniques for this, like using robust statistics to identify outliers, running anomaly detection to flag suspicious data points, or even having humans manually review the data.
Okay, so it's a combination of automated and manual checks.
And then you have algorithm protection, which is about making the training algorithms themselves more resistant to these attacks.
Oh, okay. So it's not just about the data, it's about the process too.
Right. So this could involve using algorithms that are less sensitive to outliers or developing methods to detect and remove backdoors that attackers might try to insert.
So it's about building a more secure learning process.
Exactly. And then the last one is robust aggregation, which is really important in distributed learning settings like federated learning.
Okay, yeah, that's where multiple parties are working together to train a model.
Right. And with robust aggregation, you're basically designing ways to combine the updates from all the different participants in a way that can identify and ignore any malicious contributions.
So you're making sure that the final model isn't corrupted by bad data.
Exactly. It's like having a system of checks and balances to keep the whole process honest.
Very cool.
Okay.
Okay, so we've covered data sanitization, algorithm protection, and robust aggregation for poisoning attacks.
Right.
What about adversarial attacks? How do we defend against those sneaky perturbations?
Well, the paper goes into a whole bunch of different strategies. It starts with this idea of model robustness, which is basically making the model less sensitive to those tiny changes.
Okay, so if you can make the model more stable, then those little perturbations won't have as much of an effect.
Exactly. And there are a bunch of different ways to achieve that, analyzing the network structure to identify and fix vulnerabilities, extracting what are called DNN invariants, or developing methods to formally verify the robustness of neural networks.
So it's about strengthening the core of the model.
Right. Making it more resistant to those subtle manipulations.
Okay, what else?
Well, then there's this really cool idea called adversarial training.
Oh, yeah, I've heard of that one.
It's basically like giving the model a vaccine. You expose it to adversarial examples during training so it learns to recognize and ignore them.
So you're training it to fight back.
Exactly. It's a really effective technique.
What about those input reconstruction techniques?
Yeah, so those are all about trying to clean up the input before it even reaches the model. Trying to remove or reduce the effects of those adversarial perturbations.
So it's like having a filter that removes the noise.
Exactly. And there are a lot of different methods for this, like image denoising techniques, JPEG compression, or even more sophisticated approaches that take advantage of what we know about how those perturbations are created.
Okay, so it's about making sure the model's getting a clean signal.
Right. And then there are also data preprocessing techniques like feature squeezing and random pixel removal.
Okay, how do those work?
Well, they basically try to reduce the effectiveness of the adversarial perturbations by changing the input data in a way that still preserves the important information, but makes it harder for attackers to craft those perturbations in the first place.
So it's like scrambling the input in a way that the attacker doesn't expect.
Right. Exactly.
Yeah.
And finally, there are ensemble methods, which are all about combining multiple models together to create a more robust system.
Okay, so it's like having a team of experts instead of just one.
Exactly. And by using different architectures, different training data, or even different defense mechanisms, you can make it much harder for a single attack to bring down the whole system.
That's a great approach. So we've covered a lot of ground here. We've talked about model robustness, adversarial training, input reconstruction, data preprocessing, and ensemble methods.
Yep.
It seems like there's a lot of promising work being done to defend against these adversarial attacks.
Absolutely. And this brings us to a really important point that the paper emphasizes throughout:
What's that?
the importance of interpretability and explainability in deep learning security.
Yeah, we've been talking about that a bit throughout this conversation, but why is it so crucial in the context of security?
Well, because if we want to build trust in these AI systems, it's not enough for them to just be accurate,
Right. It's like a black box. We don't know what's going on inside.
Exactly. We need to be able to understand how these systems are making decisions.
To see the reasoning behind the output.
Right. And that's not just important for debugging and improving the models. It's also crucial for making sure that they're behaving in a way that's fair, unbiased, and accountable.
Okay, so it's about transparency.
Exactly. And that's where interpretability and explainability come in. Interpretability is about understanding how the model works internally. And explainability is about being able to provide human understandable explanations for specific predictions.
Okay, I see the distinction.
And the paper highlights a lot of the research that's being done in this area. Techniques for visualizing model activations, methods for attributing predictions to specific features, and even designing models that are inherently more interpretable from the start.
So it's about shining a light on the decision-making process.
Exactly, making it more transparent and accountable. And this transparency is crucial not just for building trust, but also for detecting and preventing security threats.
Because if you can understand how the model is making decisions, you can better identify potential weaknesses.
Right. And the paper specifically mentions things like reluplex and reluval, which are tools for formally verifying the robustness of neural networks. And also techniques like abstract interpretation, which are used in systems like AI2 and Deep Stellar to analyze and prove the security of these models.
So we're using math to make sure these models are behaving themselves.
Exactly. It's about bringing that rigor and that transparency to the field of AI security.
I like it. So it sounds like we're moving towards a future where AI systems are not only intelligent, but also more understandable and accountable.
That's the goal. And it's not just about security, it's about making sure that AI is developed and deployed in a way that's ethical and responsible.
I think that's a perfect place to transition into our final part of this deep dive, where we'll wrap up and discuss the key takeaways for our listeners.
Sounds good. Yeah, I think the biggest takeaway from all of this is that deep learning security, it's not just someone else's problem, you know?
Right. It's on all of us.
Exactly. Everyone who's involved in the development, the deployment, the use of these systems, we all have a role to play in making sure they're secure.
It's like we need to bake security into the entire process.
From start to finish.
Yeah.
From data collection and pre-processing to model training, evaluation deployment, the whole 9 yards.
So it's a shift in mindset.
Oh,
We need to stop thinking of security as an afterthought.
right. It needs to be front and center.
And what does that look like in practice? For our listeners out there who are, working on the cutting edge of deep learning, what are some concrete steps they can take to improve the security of their systems?
Well, I think the first step is to really understand the risks. Do a proper risk assessment. Figure out which threats are most relevant to your specific application and your data.
Okay, so assess the landscape.
Exactly. And then once you have a good understanding of the threats, then you can start looking at the different defense mechanisms that we talked about and figure out which ones are going to be most effective for your situation.
Because there's no one-size-fits-all solution.
Right. It's all about finding the right combination of techniques for your specific needs.
So it's about tailoring your defense strategy to the specific threats you're facing.
Exactly. And don't be afraid to experiment, Try different things. See what works. The field is moving so fast that what's considered state-of-the-art today might be outdated tomorrow.
So stay curious, stay up to date.
Exactly. And share what you learn with the community. The more we all know about these threats and how to defend against them, the better off we'll all be.
It's a collaborative effort.
Absolutely.
Well, this has been an incredible deep dive. I mean, we've really gone deep into the world of deep learning security.
Yeah.
And it's clear that these systems are facing some serious challenges.
Oh, yeah. The threats are real. But the good news is that the defenses are evolving, too.
Right. It's an arms race.
It is.
Yeah.
But it's a race that we need to win if we want to build a future where we can trust these powerful technologies.
I think that's a great note to end on. With great power comes great responsibility.
Absolutely.
As we continue to push the boundaries of AI, we need to be mindful of the potential risks and take proactive steps to mitigate them.
Couldn't agree more.
Well, thank you so much for joining me on this deep dive into deep learning security. It's been a pleasure exploring these complex and important topics with you.
It's been my pleasure as well.
And to all our listeners out there, stay curious, keep learning, and build responsibly. We'll see you next time.